How's that? Okay, shall I begin?
Please.
Yes.
Yeah, go
All
ahead, please.
right, this time I hope the audio works well. Um, I'm very excited to give a talk about the status of the search for extraterrestrial intelligence called SETI. And I titled the talk When I'm 64 because we humans have been searching for intelligent life in the universe for 64 years. And I'll show you how that worked. Back in 1959, there was a famous paper by Cocconi and Morrison published in Nature with the title Searching for Interstellar Communications. And you see their prediction. They predicted that we humans should search for radio band frequencies from 1 megahertz to 10 gigahertz as the best choice for the electromagnetic communication that other civilizations would use. This was logical, of course, because at that time we humans used radio wave communications for most of our communication on the Earth. So that's what's happened for the last 64 years. There have been actual radio wave observations using the world's largest radio telescopes, frequencies between 100 megahertz and 10 gigahertz. And a survey has been done for 64 years of almost 1 million stars, as I will show you. So this is quite an interesting moment in history, 64 years of searching for intelligent life. The paper that came out 3 years ago by the Breakthrough Listen group, you see, came out in 2020, but they came out with a new paper just a few months ago. You see, 2023. And in that paper, they summarize the status of searching for radio waves from extraterrestrial intelligent life. Here's how they searched for 300,000 stars for their intelligent communications. They used the Large Radio Telescope Green Bank in the United States and the Parkes Telescope in Australia, and they used them for 8 years. They surveyed 300,000 stars by using a trick, and I want to tell you what that magic trick is. They established a set of target stars, 1,327 stars of all spectral types. Here's where they are in the sky, a sky map showing where all of their target stars were, again observed by Green Bank and Parkes radio telescopes. They surveyed for frequencies 1.1 to 1.9 gigahertz and 2 to 4 gigahertz. Those are the radio wave frequencies. And they had a detection threshold of 10 to the 13 watts. In other words, 10 terawatts. Another civilization around any of those 1,300 stars that was beaming a radio frequency signal toward the Earth with a power of 10 to the 13 watts, we would have detected. This is quite impressive because, of course, 10 to the 13 watts is not that much. We humans use much less than 10 to the 13 watts routinely here on the Earth. Now, of course, out of those 1,326 target stars, they had 0 detections. You know this because if there were a detection, you would have heard about it. It would have been on the front page of the cover of Der Spiegel and the cover of the New York Times. But of course, there's been no announcement in Der Spiegel about radio waves. And so there is a non-detection. It's an important, firm non-detection of radio waves coming from extraterrestrials with an upper limit of 10 to the 13 watts. That tells you that the fraction of stars emitting 10 to the 13 watts is less than 1 out of 1,326 stars, or in other words, less than 1/10 of 1%. This is a great non-detection. I love non-detections because it's not hype, it's not a lie, it's not somebody trying to trick you like UFOs. This is a real non-detection, and you can agree that out of 1,000 stars or so, none of them were broadcasting 10 to the 13 watts or more toward the Earth. But there's more. In every radio beam from a radio telescope, there are other stars, background stars, because of the width of the radio wave sensitivity. And that means that when the radio telescope was observing the target stars, each one of the target stars has hundreds of background stars located behind each target star. Here's one example. This is Hipparcos 109426. You see the target star, but way in the background are other stars. And of course, we now know none of them were broadcasting radio waves because we had no detections. However, they were farther away. So the power, the radio power, would have had to have been, it must be greater in order for us to detect those more distant advanced civilizations. Now, here's a graph that shows all of the stars, the target stars in green, the background stars in red. This is the number of stars on the vertical axis and the distances to those stars in parsecs on the horizontal axis. 100 parsecs, 200 parsecs, 300 parsecs, 400 parsecs. Here in red are all of the background stars. There are 300,000 of them in addition to the original 1,300 stars shown here in the green. And these background stars, of course, have non-detections for them too. And in particular, the radio power from any advanced civilization must be greater in order for these distant background stars to be detectable. Well, we can calculate how much more radio power is required for those background stars in order for us to detect them. There's almost 300,000 of them, and we can calculate the required radio power. And here's the answer. Out of the 300,000 stars, 287,000 stars, they each have a required radio power. You can calculate that on a piece of paper. And of course, instead of 10 to the 13 watts, those background stars must be broadcasting, if there's intelligent life there, at 10 to the 14 watts or 10 to the 15 watts or 10 to the 16 watts. And here's the graph that shows all of that. This is a complicated graph, and I apologize, but it's so important I wanted to show it to you. On the vertical axis is an upper limit to the fraction of stars having a certain radio power. The fraction could be 1 out of 1,000 or 1 out of 10,000 or 1 out of 100,000. And on the horizontal axis is the required radio power. Here again is 10 to the 13 watts, less than 0.1%. 10 to the 14 watts, there's a lower upper limit, 10 to the 15, 10 to the 16, 10 to the 17 watts. And I can now tell you, based on this graph, that because there are 300,000 stars, the upper limit at 10 to the 17 watts power from ET is less than 0.0003%. In other words, less than 0.0003% of stars are emitting radio waves of 10 to the 17 watts or more. Now, that's amazing because an advanced civilization with greater technology, let's say 1,000 years advanced compared to us, or 1,000,000 years advanced compared to us, an advanced extraterrestrial civilization would have no trouble broadcasting 10 to the 17 watts. A simple, nuclear power plant could do this from an advanced civilization, but they did not. So this is the first and very recent upper limit to the radio broadcasts of extraterrestrial civilizations. You could observe 10 times more stars, and all that would happen is that this upper limit line, this now red line, would go down a little bit. So there would be, you could put a limit that's a little lower than 0.0003%. But the general astronomy community does not realize that these radio wave searches for extraterrestrial intelligent life, these searches are now very powerful. They are telling us that advanced civilizations emitting 10 to the 17 watts are rare, very rare, and even 10 to the 13 watts are rare. So this is extraordinary. Now, let me move to a topic that is even more interesting. We know that our current communication on Earth is being done by fiber optics. Using optical light is a better way to communicate, and also using lasers. And this was first suggested in 1961 by Schwartz and Towns. They said, and I will quote here, "A civilization out there could be 1,000 years ahead of us," Towns said. "It seems possible that some being, in other words, a life form, on a planet orbiting a nearby star could send a bright enough laser beam that we could see it." So the search now has turned to looking for laser beams from advanced civilizations. And of course, we humans are already using laser communication for our satellites. So it makes sense that other civilizations would use lasers. There's a lot of reasons to use lasers. They give you higher bandwidth for information transfer, and they give you privacy. And of course, the laser beams travel for thousands of light years. So searching for lasers makes sense. And indeed, there might be a galactic internet, some kind of network of laser beams among the civilizations in our galaxy. And if you build a telescope that's looking for those laser beams, you might intercept one of them. And that's what we've been doing for the last 10 or 15 years. A group that started this was Andrew Howard and Paul Horowitz at Harvard. Here are two papers where they looked for laser pulses, and they searched all over the sky, 4,000 stars, 1,500 hours of observation time. And after their survey was finished, they found nothing. This was unfortunate, but it was a great attempt. More recently, we have been looking for lasers from ET by looking directly at the spectra of other stars. Maybe another star has an emission line, and the emission line is actually from a laser from the civilization that lives near that star. We used the Keck telescope in Hawaii, 10-meter aperture. We observed, this is my group did this, we observed 5,600 stars. We used the large spectrometer on the Keck telescope. Here's what the spectra looked like. It's a so-called Echelle format. We looked for laser light in any of the spectra of 5,600 stars. And here you see where all the stars are in the sky. They're scattered all over. We could not observe the southern hemisphere, of course. Here's the Kepler field, the Kepler spacecraft field. We have a lot of stars there. So we observed 5,600 stars for laser light in the spectra of those stars. Nothing. We looked very, very carefully. We published a lot of papers. We didn't find anything. I want to now tell you our most recent try to detect optical lasers from ET. Here we built our own telescope, and we built a telescope that you can build yourself. We observed more stars, and indeed we observed, we looked for lasers in between the stars. The way we did it was very simple. We took an amateur telescope and we put a prism in front. You can buy a prism, put it in front of your telescope. We did it for a larger amateur telescope. This, you may be familiar with this. This is a telescope Celestron makes. It's called a RASA, R-A-S-A. And I commissioned a custom prism. You see the wedge shape of the prism to put in front of the telescope. There you see it on the right. You can take your amateur telescope, put a prism in front of it, and start taking spectra. Here's my telescope. There's the prism in front. There again is the prism in front. And now your entire telescope becomes a spectrometer. But it's a wide field spectrometer. You detect all of the stars in the field of view, except instead of getting a point for each star, you get a spectrum. And here's what the Pleiades looks like. This is from my actual telescope, a 1/4 second exposure. These are the Pleiades stars that all of you know, but instead of getting a point for each star, we get a spectrum. I put a color camera on my telescope just to show the actual spectra, blue, green, yellow, red. All the optical wavelengths are there. Here is the Ring Nebula. This is wacky. This is crazy. This is the Ring Nebula. Why does it appear twice? Here are the stellar spectra nearby. It appears twice because the Ring Nebula has two dominant wavelengths, H alpha, Balmer alpha from hydrogen, and the oxygen lines 4959 angstroms and 5007 angstroms over here. So the Ring Nebula appears twice because they are at it emits light at two different wavelengths. And actually H beta, Balmer beta, is also there faintly. So this shows you that if there were an advanced civilization in our galaxy and it was emitting monochromatic light at just one frequency, one wavelength, i.e. from a laser, we would have detected it just like we can detect the Ring Nebula. We surveyed the entire galaxy, the Milky Way plane, for these lasers. This shows declination, right ascension, the whole sky. Here's the galactic plane. These little squares show you where I pointed my telescope, this telescope here. I pointed it at each one of the fields of view. This took about a year to observe each one. I took 600 exposures, 1 second each. Why 1 second? Because maybe the lasers are only on briefly, like for a millisecond or a second or 5 seconds. I did find some candidate lasers. Here's one. This is a sequence of 1, 2, 3, 4, 5, 6, 7 consecutive exposures, and it's a zoom. During the 7 consecutive exposures, something came in the upper left, here, 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 here. What in the world crossed through the field of view with these interesting spectra? Well, the answer is it's an airplane. It's just an airplane. Airplanes have lights of different wavelengths. They even have narrowband filters over the lamps. And I convinced myself by taking a spectrum, there it is magnified. This is what an airplane looks like through a telescope that has a prism over the front. It's not an extraterrestrial laser at all. Here's what the spectrum, I can tell you the spectrum of this had a very definite xenon. If you see down here, I was able to analyze the light. You can see little faint emission lines here and here and here and here. That's xenon. And guess what? airplanes have xenon lamps. So this is just an airplane with many, many lamps, and it crossed through our field of view. I found some other laser candidates in the survey. You see here a very bright emission line. It looks like it could be a laser, but it's not. This is just a Wolf-Rayet star. Some of you have heard of Wolf-Rayet stars, I'm sure. They're luminous, supergiant stars, and this just showed up in our survey of the Milky Way plane. Of course, this proves that we would have detected lasers because my automated software found this Wolf-Rayet star, but it's not a laser. So we surveyed the entire galactic plane and we found nothing. And let me remind you, we were not only surveying stars in the Milky Way plane, we were observing the space in between the stars. There could have been spacecraft, probes, colonies. There could have been objects within our solar system. We didn't find anything. So we've now published 2 papers about the search for laser light from the galactic plane with nothing. So we have no detections either at radio wavelengths or at optical wavelengths. So we're going to try something new. And I'm going to end my talk by telling you what we are doing now. And it'll take me 10 minutes to tell you what we are doing now to search for ET. We've changed our focus. We are now going to look for extraterrestrial probes nearby, perhaps in our own solar system. Maybe they are here. Maybe the probes are here hiding from us. They came here 100 years ago, 1,000 years ago, 1,000,000 years ago, and they're orbiting the Earth, orbiting the sun, watching us. And we should try to find those probes that are already here. So we're going to search. Stefan Geier is a part of our team. You see his name here. Beatrice Villarroel is the principal investigator. And we're searching the solar system for glints off of the space probes from ET. Maybe they're emitting lasers in their communication. Maybe they have parked on an asteroid and we can detect the glints or their lasers when they've parked on an asteroid. Or maybe some asteroids actually are spacecraft. After all, we humans know about 1 million asteroids. How do we know they're asteroids? Maybe what we think is an asteroid is not an asteroid. We wouldn't know because it's 16th magnitude or 18th magnitude. So we are going to observe all of them. And the idea behind our new program is to put 2 telescopes somewhere on the Earth, have them synchronized and observing the same spot, and look for flashes of light that could be verified by virtue of both telescopes observing that region. And if it's near enough, for example, in our solar system, we would get parallax because there's 2 telescopes. So we could measure, you see here, we could measure the distance to the extraterrestrial artifact, the probe, the laser, whatever it is. We can measure the distance by the parallactic angle. So that's what we're going to do. But there's more. We're going to not only confirm and get parallax, we're going to add a 3rd telescope that has a prism. Why not have a 3rd telescope with a prism so that we get a spectrum of the flash of light, real time, simultaneously? So that's the goal, is to build a system that has 3 telescopes, giving us confirmation, parallax, and a spectrum, all operating, of course, synchronously, simultaneously. We plan to start by putting the 3 telescopes in California, one in where I live in Santa Rosa, one in the Sierra Nevada mountains. Here's the Sierra Nevada mountains, and one at a college where one of us is, one of my colleagues is a professor. So we're going to start with the 3 telescopes there. We want to purchase a new telescope built by a company called Planewave. It's called a Delta Rho 500. It's wide field, 2 degrees. The field of view is 2 degrees. This is what it looks like. We will purchase a camera from Beijing, from China, QHY 411. It has 151 megapixels. Let me repeat that, 151 megapixels. It's an amazing new camera, just came out. We'll take 1-second exposures and look for flashes of light from ET probes anywhere nearby. So we've already built a prototype. This is, again, a RASA prototype. There's the QHY camera, a piggyback telescope as the second telescope. So we're already starting this. So let me summarize by saying there's bad news, but in a way it's also brilliant. 64 years of SETI, nothing. It's profound, because if you read the newspapers or the magazines or watch blogs, you might think there are UFOs everywhere and ET is everywhere, but in fact, the professional efforts have found nothing. But we're going to search a new way. We're going to search our solar system for probes that are already here, and we're going to look for glints of sunlight, laser beams from them, maybe machines on asteroids, and hopefully we'll be able to turn this around and make a detection within the next 5 or 10 years. So I think I'm going to stop there. That's my talk. Thank you very much.